We have, up to this point, studied limits of functions with one independent variable. In other words, what we've studied is this, the limit as x goes to a, something that looks like this. But now what we want to do is we want to build on that and study things like limits of functions with more than one independent variable. Maybe in this case, two independent variables, x and y, and we want to figure out, well, what does that mean? In other words, we realize what this means, we want to build on that and see if we can define this. Now, first of all, I want to revisit the limit with functions with single variables, just to be sure we all understand where, so that we can be more clear on what this is. So let's look at the single variable limit. Just refresh our memory here. Let's suppose that we've got some curve up here, and we've got some number down here on the x-axis, and this is f of x. And I'm going to say this over here is L on the y-axis. Remember, what we talk about is we talk about the limit as x goes to a, let's say from the right. And what that means is, just imagine you're on this curve and you're being pulled along. It's as though you're tethered to this x-axis, something on the x-axis that's approaching the a. And you are just connected up here, stuck to the axis. Well, as x goes to a, what do you get? What do you get closer to? The height. What's the height you get closer to? Well, L in this case. So we say the limit as x goes to a from the right is L, and we could do the same thing going from the left. We'd say, okay, let's suppose now x is approaching a from the left and you're stuck on this graph. Where do you end up? Well, you end up at L. Now, because you end up at the same place coming from both directions, and there are only two directions here, coming from the left or coming from the right, we say, well, we can talk about that limit existing and being L. Now, that's not always the case where you end up at the same place coming from left or right. So let's try this one. Let's play the same game here. We've got x, we've got y, and we'll put a curve in here. Maybe coming up here, and then here. And here is A. Now I'm going to call this point that corresponds to this little hole, I'll call that L1, and I'll call this L2. Now you can see, if we talk about approaching from the right, we end up over here at L2. If we talk about approaching from the left, we end up at L1. Those are not the same. We don't have the same vertical values. So what we would say is, we would say, well, in this case, the limit as x goes to a, we just say it does not exist, because you have to end up at the same place coming from the left or the right. In single variable, there are only two directions, right and left. You approach from that way because you're on the x-axis. Now, to be a little bit more rigorous in talking about limits, we want to go back and talk about the definition. So let's do that. Let's look at precisely what does this mean when we talk about the limit as x goes to a of f of x equals L. And this will help us to understand the definition involving more than one independent variable. So here we have the graph just like before, and I suppose this is the function f of x, and I've got a down here, and let's suppose this is the limit. So we say the limit as x goes to a of f of x equals L. Well, here's what that means. If we go up a little bit above L and the same distance below, so that we have L plus epsilon here, L minus epsilon here, that's going to correspond to some values on the x-axis. Now, what we want to do is come up with a neighborhood on the x-axis, and if you look at this, if you look at the distance from A over to this point and from A over to this point, I'll just choose the shorter of those two. And here's what I get. I get a little neighborhood that may go, something like that. And the distance from A, this distance right here, I'll call that delta. So what we have here is we have a delta neighborhood that corresponds to this epsilon neighborhood up here. Now the idea is that any x value I choose in here, let's say I choose that one, it's in this neighborhood. If I go up and I come over, notice I'm within that epsilon neighborhood. So so we say this, if x minus a, if that distance is less than delta, then you know that f of x minus L is less than epsilon. So using this, we can write out the formal definition. This right here means, so this limit, the limit as x goes to a, equals L, precisely what that means is that let me write this out, means that for all epsilon greater than 0, there exists a delta greater than 0 such that this happens whenever this happens. And that's how we define a limit in single variable. Okay, now, I want to discuss now the multivariable, where we have more than one independent variable. Okay, so here we go. Now, let's suppose that, so in other words, what we want to do is we want to figure out what this means. We want to figure out what that means. Well, since we're in 3 dimensions now, it's a little bit more complex because, let me just draw a picture. Let's suppose we've got a function, and let's just look here. Now, I'm going to just draw an xy axis, and you've got this surface up here that's above the xy axis, and it's defined over some region here. Okay. Some region down here on the xy axis. So this little region here is full of ordered pairs, and we plug those ordered pairs in, like if we plug in this ordered pair, x1, y1. It corresponds to some number on the z-axis, which I'll just write this way. It corresponds to maybe this right here. Some z value over here. So let me mark that. Okay. So this is f of x1, y1. Okay. That's what that is. So let's suppose we have that situation. Now, let's suppose that inside here somewhere, I've got a point x0, y0. And I'm going to draw a circle around that. I make it, pretty big just so we can see it. And let's suppose this circle has a radius of delta. Now I'm going to come over here and I'm going to say this is a limit. This is the limit. And this limit here is the limit as xy goes to x0, y0 of f of xy equals L. That's what that is. Now, here's what I'm going to do. I'm going to go up a little bit, just like before. I'll say this is L plus epsilon. This is L minus epsilon. And what we're going to say is that we're arguing the same way. We're saying that if you come back here, no matter how we choose this epsilon, no matter how we choose it, it boxes in some function values here. And that corresponds to a delta neighborhood over here, which I'm representing as a circle, or a disk. Now, actually, when we write out the definition, it's going to be like a broken neighborhood. But anyway, that's not so important right now. So we're saying this, that if I pick any point in this delta neighborhood, it's going to give me a function output in this epsilon neighborhood. So no matter how I choose epsilon, I can find a disk over here. No matter how I box in L, I can find a disk to encircle about the point so that every point in that disk will give me an output over here in this epsilon neighborhood. So let's see if we can write it out formally. Okay, so here we go. Let's write it out formally. The limit as xy goes to x naught, y naught equals L means, and we start this off just like before, for all epsilon greater than 0, no matter what epsilon I choose, there exists a delta greater than 0 such that this is true. This right here, f of xy minus L less than epsilon, happens whenever this is true. Now, the way we write this looks a little different. We don't have the absolute value. We actually have the distance formula. We say this is, instead of the absolute value, we're going to have x minus x naught squared plus y minus y naught squared is less than delta. So that's the formal definition. Okay? And that's when we have two independent variables. Now, there's a couple of things I need to define here. Okay? And it will help us to maybe understand, just speak the same language anyway. Let's suppose that I have, let's just talk about a disk. I talked about a disk up there, a circle, and I'm going to put two circles here. I'm going to say this one right here is centered at x naught, y naught, and I'm going to say it has a radius of delta. And I'm going to say that this one over here, I'm going to say that here's a circle as well, but notice it's a broken circle. Okay, so, and I'm going to say it's centered at maybe x naught, y naught, the same, and its radius would be like delta. It's not, the boundary is not there, but we'll just denote it this way. Now, this right here, we're going to refer to as a closed disk. And this one right here we'll refer to as an open disk. So if I ever say a closed disk, I'm talking about a circle like this. And if I say an open disk, I'm talking about a circle like this. Now, there's a difference in the way that we present them, or the way they would be described mathematically. This one is going to be x minus x naught plus y minus y naught squared, and that's going to be less than or equal to delta, because it contains that little boundary point, that little boundary there. Now this one over here is going to be x minus x naught plus y minus y naught, and it's going to be less than delta. So you can see a little bit different ways that we would present those. So closed disk, open disk. Now, I want to use that to talk about interior points and exterior points, and boundary points. So let's do that. Let's suppose that we go back to our little region here. Okay. And notice this is a closed region here. I've got a boundary going around it. And I want to define what I'm talking about when I say an interior point. So For example, this right here is clearly an interior point of that region. There's no question about it. You can just look at it and see. But what we want to do is define it more rigorously. So I'm going to say this is x1, y1. Now, if x1, y1 is an interior point, here's what it means. It means that we can find a delta, a disk of radius delta, so that every point in that disk also lies inside the circle. So let's just look at delta here. Now you can see that every point inside that disk is also inside the circle. I mean, every point inside that disk is within this R. So if that happens, in other words, I have x1, y1. I want to know, is it in the interior? And the answer is, well, can you draw a circle around it so that every point in that circle is also in the region? Okay. So what we've done here is we've drawn a circle, and you can clearly see that every point in that region, or in that circle, is also in the region. Therefore, x1, y1 is an interior point. Now, it doesn't matter, so maybe we'll get really close over here. As long as we can draw one disk around that point so that every point in that disk is also in the region, we say that that point is an interior point. Okay, that's what we mean by interior point. Now, if we talk about a boundary point, let's suppose we've got a point here on the boundary. Now, a boundary point is this. It's a point such that every disk that we draw around where that point is centered, in the center of the disk, every disk we draw will have points that are both inside and outside. Whenever we have that situation, we say, okay, that's a boundary. Okay, so we're looking at this region. We've defined interior points, and we've defined boundary points. Now, a region is considered to be closed if it contains all of its boundary points. It's open if it contains none of its boundary points. Now, in other words, if every point is interior. Now, a region can be neither closed. You can have a situation where you have a region that contains some, but not all of its boundary points. And in that case, we'd say it's neither closed nor open. Okay, so that is just some terminology that will help us to, have the same vocabulary. Maybe that would have been better to introduce before the definitional limit. I don't know. But anyway, this is if we have a function with two independent variables, and we're looking down from the z-axis down on the xy axis. Now, let's suppose we want to expand that to functions with three independent variables, like a f of x, y, z. So let's just look at this. Let's suppose that we've got this situation. We've got a function like f of x, y, z. And there we have three independent variables. Now, it's not like we're looking at the xy axis to get numbers to plug into the function. In fact, we're looking out here in space for ordered triples to plug into the function. Now, if you transition to space, you're no longer talking about disk inside a region. You're talking about spheres. And you're talking about these, maybe an open sphere would be this. It would be x minus x naught, y minus y naught, and z minus z naught. And an open sphere of radius delta would be that. A closed one would be less than or equal to. Now, so just like we had the region on the xy axis, in space you might think of something like a cloud. So if you look up at a cloud and you think about, okay, is a point interior to that cloud or exterior? Well, if you can draw a sphere around that point so that every point within that sphere is also in the cloud, you would say, okay, that point is interior to the cloud. If if every sphere, on the other hand, contains points inside and outside that cloud, you say, well, that cloud, that point is on a boundary. Now, what I want to do at this point is just get right into how do we evaluate limits with more functions with more than one independent variable. And really, for the most part, what you do is you remember all that you've studied about limits before. When you're talking about evaluating limits, remember you had limits like this. You had the limit like as x goes to 4 of maybe x squared minus 16 over x minus 4. You would have a limit like that. And notice that if you plug in, you get 0 over 0, so you know that tells you you've got a little work to do. So remember what we did, we tried to simplify it. And we did that by factoring. And notice that this cancels and our limit is 8. Now, it wasn't always that we had to factor and cancel or do some kind of algebraic manipulation to evaluate a limit. Oftentimes, we could just plug in. So like if we have the limit as x goes to 3 of 2x plus 1 over 3x minus 2, we can just plug in. So this is going to be 7, and this is 9. 7 is 1. It's like 9 minus 2. Yeah, so the limit is 1. So whatever you know about limits before, all the properties that you've studied, you keep those in mind. But now we're going to look at, well, what happens when you do get 0 over 0 and you can't factor and cancel and get something that works out? Well, let's look at one that you can real quick here. Let's look at one. Let's look at this. Let's suppose that we've got, this will be our first limit that we've looked at in with two independent variables. Let's suppose that we've got this limit. Let's suppose that we've got 1, well, let's do that, 1, 1. And let's suppose that this is x squared minus y squared over x minus y. Now, the first thing you try to do is plug in, just like usual. And what you're going to get, of course, is 0 over 0. So that tells you to go forward and try something else. So here we go. Let's take the limit. xy goes to 1, 1. I'm going to factor. And those cancel, and now I can plug in and I get 2. So this is just like before. We've done this kind of thing a lot. Now let's look at a little bit different of a problem where we plug in, we get 0, 0, and then if we try to factor and cancel or simplify it in some way, we can't. Let's look at this one. Let's suppose that we've got the limit as xy goes to 0, 0. And let's suppose that our function is x squared minus y squared over x squared plus y squared. Something like that. Now, of course, if you plug in, you get 0 over 0, and you can't factor the bottom. You can factor the top, but it wouldn't do you any good. So you suspect that possibly this limit doesn't exist. And what we have to do is we have to show that. Now remember, this limit is not going to, remember single variable. If you approach from the left and if you approach from the right, you get two different values for your limit, then you say the limit does not exist. Well, now we don't have the left and the right. We have literally infinitely many directions that you could approach x, y, 0, 0. So you have these just infinitely many paths to get to 0, 0. So what you have to do is find at least two paths that give you a different result. So let's see how that goes. Let's see if we can find a couple of different paths. So here we go. We've got the limit, and as xy goes to 0, 0, And let's see about if we can find two different paths. So here's what I mean. Let's suppose that we approach 0, 0 on the x-axis. So in other words, I'm going to approach along the x-axis. Well, if I approach along the x-axis, that means that y is 0. That's what that means. That means that y is 0. So let's look at this limit, but let's replace y with 0. And here we have it. We have the limit xy goes to 0, 0. And I have x squared over x squared. Well, that's 1. So if we approach 0, 0, and we're approaching along the x-axis, then our limit is 1. Now, so that's what we get when we approach along that path. Now let's look at this. Let's suppose that we want to approach along the y-axis. Okay. So let's go along the y-axis. And that means that x is equal to 0. So here's what we've got then. We've got the limit as xy goes to 0, 0. And our function is now negative y squared over y squared, which is negative 1. Now, 1 and negative 1 are different. So apparently, the limit, it matters which way we approach 0, 0. So we would say that that limit does not exist because we found two paths that simply won't work, or they give different values. Therefore, the limit is not going to exist. Now, our work there is sufficient for us to conclude that that limit doesn't exist. But there are a lot of different paths that we could have chosen. For example, I could have said, well, let's go along the line y equals mx. I could say, okay, let's just go along that line. I'm not specifying what m is, but any line, y equals mx, passes through the origin. That's what we have to remember. Every path that we choose has to pass through the 0, 0. Y equals mx, yeah, it passes through 0, 0. It has to have that point in it. So if we're going along that path, let's see what we get. Okay, so here we go. We've got the limit and what I've got now is I've got x squared here, and in place of y squared, I'll just put mx. So I've got m squared x squared. And of course, down here, I got x squared plus m squared x squared. Now, you can see what happens when we do that. We can factor out an x squared, and we get 1 minus m squared. And down here, I can factor out an x squared. I get 1 plus m squared. Now, if you look at this, our x's, y's, they're all gone. And it looks like what we have is a situation where we get a limit here. Okay, so this is the limit. It's just going to be 1 minus m squared over 1 plus m squared. There's no x's or y's to plug in. So there's our limit. Depending on how I choose m will give me a different slope. For example, if I choose m to be 4, well, if m is 4, in other words, if I approach along the line y equals 4x, here's what I would get. I would get 1 minus 16 over 1 plus 16. Well, that's negative 15 over 17. So that's one limit, whereas if I chose m to be 3, I would get 1 minus 9 over 1 plus 9. And that would be negative 8 over 10. So I get a different limit. So that's one way. This just shows that, you know, however we choose the line, whatever slope we choose, we're going to get a different limit. Okay, now let's try one, a limit with uh, three independent variables. So let's suppose we've got the limit, and now we have x, y, z, and let's suppose it's approaching 0, 0, 0. And let's suppose that we have, let's say 2x squared plus 3y squared and plus z squared. And down here maybe we have x squared plus y squared plus z squared. Now, of course, if you try to plug in the 0, 0, 0, you get 0 over 0. So here's what we want to do. We don't just have x's and y's, we have x, y's, and z's. So let's do this. Let's, just like we did earlier, where we said, okay, let y equals mx. We'll just approach along that line. Let's do the same thing here, but this time let's choose our, let's get our line that out. Let's do the procedure that we use for 3 space. In other words, I have a vector to which the line is parallel. And the point that it passes through, of course, is 0, 0, 0. So I want to make a vector, a set of parametric equations for this line that's parallel to that vector. So I get x equals at, y equals bt, and z equals ct. Whoops, ct. Now, I want to plug in those values. And this is what I'm going to get. I'm going to get the limit, and now it's as t goes to 0. And here's what we would get. We would get 2a squared t squared plus 3b squared t squared plus c squared t squared. If I just put that in, all I did was put it in for x, y, and z. And now down at the bottom, I get a squared t squared plus b squared t squared plus c squared t squared. Now, I want to see about evaluating that limit. Well, I'm going to factor out the t and divide. And here's what I get. If I do that, then I get something without t's. I get this. I get 2a squared plus 3b squared plus c squared. And down here, I get a squared plus b squared plus c squared. In other words, I just get the components of my vector. Well, that limit right there is going to depend, and let me just erase the limit. That is actually the limit. This right here depends on our choice for vectors. So if we approach 0, 0, 0 using the vector, ABC, where the vector ABC is maybe 1, 2, 3 or something, then that's going to be, we're going to get a different limit than if we choose the vector -4, 5, 7. In other words, how we approach 0, 0, 0, if we're approaching on the line that's parallel to the vector ABC, depends on our choice for the vector ABC. So we would say that limit does not exist.